Hello, everyone. I hope everyone's having a good day. Today, we're going to be talking about atomic masses. So, here we go. A little share screen. And let's take a look. And just to remind everyone, before we had said that the mass number equals the sum of protons and neutrons, right? And we know that you can't have half of a proton, you can't have half of a neutron, right? So what I want us to do, let's take a look quickly at our periodic table because something weird is going on. Let's look at all of the atomic masses of any of these numbers, right? And if we look at all of them, we will notice that any one of these atomic masses, most of these, if not all of them, I think all of them on here minus these guys down here, which are weird, right? They all have decimal atomic masses, even though the mass number is the number of protons and neutrons. Absolutely correct. You can't have a half a proton, can't have a half a neutron. Absolutely correct. So let's talk about why are there, and we're even going to have an aim today, crazy. Today's aim. Why are the atomic masses on the periodic table not whole numbers? And that has to do with how we actually calculate the atomic masses on the periodic table. See, in any sample of an element that you grab in nature, any sample, in nature inevitably will have multiple isotopes. And so the reason that we have a decimal isn't because it's actually the mass number, but the atomic mass is actually an average. Which we call the average atomic mass. And the thing about the average atomic mass is that this is a weighted mass. Weighted average. A little bit different than a regular average. And a weighted average takes into account both the mass and percent abundance, because not all isotopes occur in the same percentage. What I mean by that, that if you have a sample and you have multiple isotopes, just because of the way that nature is, inevitably some isotopes are going to be more stable or easier to create than others. easier to create, harder to destroy than others. And because of that, in any sample, you're not going to have the same amount of each. Let's look mathematically how you would calculate this. And instead of talking about isotopes, we're going to start with money. Let's say you go to the store. So we're going to go to the store, and we're going to make 4 purchases. And purchases numbers 1 through 3. So the first, second, and third purchase are $4 each. The fourth purchase is $2. You got a discount on that last one, right? And if I asked you, what is the average that was spent per purchase? You can't just do, well, you have $4 plus $2 divided by 2 equaling $2. That doesn't make any sense because we're not taking into account the fact that these 3 purchases were higher than this last one. So it's not an equal average. This isn't properly weighted. This is the unweighted average. So we know that that is going to be wrong. So how would you find the weighted average? Well, to find the weighted average of something, and I can give you the formula, it is, and I'm going to give you a key here, that for percent abundance, I'm going to write it as percent ABN. So here's my little key. I'll even write the key. Here's my key. So it's just a big old sum. So you would do percent abundance of element A. Oop. You know what? I have a better idea. Let's use capital letters. That'll make it a lot more clear. Percent abundance. So the percent abundance of the first one times its mass plus percent abundance of the second one times its mass plus percent abundance of the third one times its mass, and so on and so forth. And that's how you do the weighted average. This whole thing will equal a weighted average. So how do you find the percent abundance? Well, we see up here that there are 4 total purchases, right? 3 of the 4 purchases are this amount. So to find the percent abundance of $4, because we know that, and we're going to use this equation, we know that the mass is $4 there. The percent abundance would be 3 out of 4 purchases, right? That's the percent abundance of our first one, 3 out of 4 purchases. That times $4 plus, now over here we only have We only spent it $2 once. 1 out of 4 purchases times $2. Ah. And that is going to equal $1.50. So you spent an average of $1.50 per purchase. Notice how it's not $2, right? That is the correct way. So that's how we would find a percent abundance. Let's look at an example of how we would do it for calculating atomic mass. So what I like blue. I'm feeling some blue. How to calculate average atomic mass. Let's take a look. So let's say that there are 2 isotopes of element X. Element X35 has a mass. Oop, I'll make you a little table. So isotope mass in AMU in percent abundance. Okay, so X34, and I'm making these up, X34 has a mass of 33.96, and it has a percent abundance of 82%. Okay, and then X35 has a mass of 35.23 AMU and a percent abundance of 18%. So how do we calculate the total percent abundance? Well, we're still using this equation up here, right? But the trick to remember is that 82%, we have to make sure that's out of 100. We can't just put 82 because it's not 82 out of 1, right? If you put the number 82, that's really 82 over 1. And that makes no sense. You don't have 82 occurrences over 1 occurrences. So we have to make sure that we do 82 out of 100. So here goes the math. The first one, we're going to do 33.96 AMU times, yeah, I'll put that below. More room. Magic. Times 82 out of 100, right? Plus, and our next isotope, 35.23 times 18 out of 100. And that's going to equal 34.19 AMU. So the percent abundance of element X, I'm sorry, the average atomic mass of element X is 34.19 AMU. Now, here's a cool trick. When we're looking at the periodic table, if you're ever wondering which isotope is the most abundant, well, a cool trick is to look at the periodic table because they're all weighted averages. Whatever has the greatest percent abundance is probably, the element that is in the highest percent abundance contributes the most to the average, right? And if we look over here back at this example, we see that the number is much closer to 34 than it is 35, right? A higher average. So if we look at any of these atomic masses and we simply round to the nearest whole number, we can tell which isotope is probably the highest percent abundance. For example, zinc, probably highest abundance of 65. I can also tell that because it's 65.4, it's probably not very heavily one way or the other. As opposed to, I don't know, hydrogen, which is probably isotope 1. AMU of 1 is probably the highest percent abundant, and in fact it is. There are actually 3 isotopes of hydrogen, hydrogen 1, hydrogen 2, and hydrogen 3, and the 2 and 3 make up less than 1%, right? Carbon over here, carbon has 3 isotopes as well. Carbon 12, 13, and 14, 13 and 14 make up a very small percentage. So that is percent abundances and average atomic mass. So now hopefully you know a little bit more about why the numbers on the periodic table are all decimals. Thank you so much for watching. Have a good day. Bye.